Hi and welcome to another electrostatics lesson here in our physics class. We're looking at the net electric field. Now we have defined an electric field as the force experienced. Okay, so this is the force experienced per charge, force per charge. In other words, we had this formula that the electric field is equal to force per, and then the unit charge is just Q, where Q is a constant. Q is a constant, and that constant is equal to 1,602 times 10 to the power of -19. Okay, coulombs. That is the charge of a single particle, and we're only considering positive particles, as we are considering the electric field as the force experienced per charge, and the direction of that, because the electric field is a vector, is the direction that a positive charge will travel in, considering that a positive charge is repelled by other positive charges and attracted by negative charges. Now the force, again, where we get the force from, is the force is calculated with the formula K, charge on Q, and since it's now the force experienced by a single charge, this will the reason why this charge will experience a force is because there's another charge in the vicinity, positive or negative, and therefore this charge experiences a force, either attractive or repulsive, and around this charge exists now an electric field, because anywhere in this thing's vicinity there would be near this thing there would be a force being experienced. So Q is somewhere in here, Q is somewhere there, and as a result Q is either being repelled or attracted. And now the size of that force, in other words this force he's experiencing, depends now on the charge of Q, okay, K, which is a constant value of 9 times 10 to the power of 9, and then Q times the charge on small q divided by the radius squared. Okay, in other words, how far are these two apart? That's the radius, the distance they are apart. Now if I substitute this into that formula, it simplifies this formula to simply KQ over R squared. The Q's cancel, that Q and that Q cancel. In other words, this is usually the formula that we use for the electric field. And now what I'm going to talk about now is the net electric field. The net electric field has got to do with more than one charge. Okay, net electric field is the sum of electric fields on a charge Q. Okay, so what I'm saying is, what will happen if we put another charge Q, another charge, positive or negative, nearby this charge, so that it too has an effect. So here we have now another charge. Let's make this one yellow. Another charge that will also have an effect on Q. Now again, it depends what is going to happen. The size of this Q will now experience a force, either being attracted or repelled. So we have now two charges acting on Q, and the question is, what is the net charge? In the end, what is happening to Q? Is he experiencing a charge in the direction of Q? Is it let's say this is Q2 and that is Q1. and it all now depends on the sum of these charges. If this one, for example, is positive, it's going to repel that one. If this one is negative, it will attract him. So in other words, the force, the electric field that this charge will experience will be quite big in the direction of Q2. However, if this one is also positive, now it depends on which force is repelling him the strongest. This one is repelling him, this one is repelling him. So obviously if this one is repelling him more, the yellow one, and now it depends on, well, which one is he closest to, okay, because that also has an effect. Now it's actually very simple, but there is one thing that makes it slightly complicated, and that is that we need to consider the position of my unit charge relative to my two charges. Now there's two options that we can get. We can get that I have two charges, Q1 and Q2, and my unit charge is in between the two. Because now what would happen is that the charge that I would experience is the difference between these two charges. Notice that these two charges don't work together, they work in opposite directions. So now in this case, I would have that my net electric field is the difference between the two. For example, if this one is attracting me, and if that one is attracting me, it would depend which one is attracting me more. And I won't get the full effect of his attraction because this one takes away in the opposite direction. So I will only, for example, if this one had an electric field of 10 newtons per coulomb, and this one had an effect of 8 newtons per coulomb, then obviously the net effect is they're in opposite directions would be 2 newtons per coulomb in this direction. Notice it's the difference. So when my unit charge is between 2 points, my net effect is the charge on one minus the charge the electric field of the first charge minus the electric field of the second charge. The second scenario can be when my charge is on either side. So there's my charges, and my unit charge is now either on this side or it is on that side. Okay, the point just being that the two charges are on the same side of my unit charge. So it doesn't really matter on which side, as long as they're on the same side. This time they're working together. Okay, so if both of them are now attracting me, this one is attracting me, or the unit charge, not really me, and that one is attracting me, notice that now the effect is the sum of the two. Now again, if I, for example, have in this case, this one is attracting and this one is repelling, then notice that if this one is attracting me, it means this charge is negative, which means I will have a negative answer here, minus if this one is repelling me, it means this charge is positive, so this will be a positive answer, but in the end I will have a negative, which means I will have a negative answer minus another negative answer, which will be a bigger negative, which means my net field is greater because I subtracted twice. And that's exactly what happens. This one is repelling and this one is attracting, so they're working together to get Q in one direction. The same, in other words, their effect now is similar to this effect where we have two charges, two equal charges. So plus minus means that they have equal charges, whether repelling or attracting. So if these are opposite charges, they will have a similar effect than when these two, when in this situation I've got the same charges, where, for example, in this one, if both are the same charges, let's say both have negative charges, it would be negative something plus negative something. Notice here, two negatives, okay, being added together, two negatives being added together. Okay, so in effect, I don't want to say too much. I rather look at examples. This is just what's important. When I have charges on opposite side of my unit charge, then it's the difference between them. When I have charges on the same side of the unit charge, then it is the sum. Okay, so let's look at a scenario where we maybe have three charges. 1, 2, 3. Okay, again, it all depends on where is my unit charge. If my unit charge is here, then I will have that the net electric field is which charges are on the same side, Q2 and 3. So it's the sum of those two, Q2 plus Q3, not Q, E. The electric field produced by 2 plus the electric field produced by 3 minus the electric field produced by 1. Okay, and then obviously we're then considering this to be the positive direction because we've taken them to be the positives and E1 to be negatives. Okay, what about if I put it in here? If my charge is there, then my electric field, my net electric field, will be those that are on the same side, which is electric field produced by Q1 plus electric field produced by Q2 minus the electric field produced by Q3. Again, notice I've made E1 and 2 this direction now to be the positive direction, so they attract to force, which means they are the negative charges. Okay, and then what about if Q is here at the back? Then obviously all of them are on the same side, so the net electric field produced this time is E1 plus E2 plus E3. I made all of them positive, meaning that I take this direction as the positive direction, which means that if Q is going in that direction, Q is positive, meaning all of them would be negative. So if I'm going in this direction, I will get a net electric field that is negative. Don't worry too much about the signs, you'll figure it out. I promise. When you just think, when you answer these questions, simply think. It's not very difficult. I think for now that's it. I just want to show you this. What do I mean by this? I simply mean, remember what is our formula for E? Our formula is K times Q over R squared. In other words, E2 is K times Q2, the charge on Q2, divided by the distance between Q2 and Q, this distance between them squared. So in each one of these I will have a unique charge and I will have a unique distance. Please keep that in mind. Okay, so this is R, let's call that R2 as the distance between them, plus, so this one would be E2 would be K, E3 times Q3 divided by the distance between this charge and that Q. I was considering this Q in this bottom formula, so that would be R3. It's just I'm just giving it that footnote as it's a different distance between Q3 and R3, and then minus this one that's in the opposite direction, so this one's distance will be R1, so minus K times Q1 over R1 squared. And now even though we have these signs, they were important for my formula, but when it comes to the actual sign of the fraction, we will have to consider the charge on Q. If this Q is negative, this will obviously become a negative. If this Q is positive, it will keep this positive a positive. If this Q is negative, it will change this positive to a negative. If this Q is negative, it will change this negative to a positive. If it's positive, it will keep it as a negative. Okay, I'm sure you get the maths behind this. So now let's go and look at some examples and how we apply what we've learned to actual questions. I'll see you there.